Our pleasure to have Professor Xiang-Lei Huang from University of Michigan. Professor Huang got his PhD from Caltech. He is primarily working on radiative transfer. It's very happy for me personally because there are not so many people working on very detailed radiative transfer things. And today he is going to talk about the sensitivity of modeled far infrared radiation budget in polar continents to treatment of snow surface and ice cloud radiative properties. Let's welcome Professor Huang.
So first, I would like to thank the organized committee for inviting me, and I'll also thank the supporting staff because my paperwork is always maybe the most complicated one. So today I'm going to talk about a couple of studies we did in my group and in collaboration with the Lawrence Berkeley National Lab, so primarily Bill Collins group. And first, I would like to acknowledge my collaborators. So Hong Chen, who is my postdoc, and Professor Mark Flanner from the same department as me, and Dan Fieldman in Bill Collins group. So this is the roadmap of the talk. So I will first talk about a couple of contrasts here between the models and the reality. And specifically, the first is about the surface emissivity, and the second is about the long-wave cloud radiation. Now I will try to state a couple of facts about the far IR. And then I will talk about how we try to model the surface spectral emissivity. And then two sensitivity studies. First is try to understand the impact on the climate mean state, or rather more specifically, on the polar radiation budget alone. And the second sensitivity study is when you take this into account, what would be the implication for the teleconnections and the scenario for climate change projections, and especially for this test. So Dan Fieldman used this RCP 8.5 scenario. So basically, the talk was largely based on the paper we published early this year on GRL. And for this climate change projection, that's based on the paper we co-authored with Dan Fieldman and published on PNAS just 1 week ago. And then I will give some conclusion and thoughts. So basically, the surface emissivity is defined as this. So in the flux form, let's say how much the emission from this particular surface or whatever subject compared to the black body emission at the same temperature. But basically, it's a fractional number, non-dimensional, and it tells you the capacity of this particular subject can emit with respect to the black body radiation. So if you do a survey for all the AR4 or AR5 GCMs, and you look at the radiation scheme just in the atmosphere model alone, you will see this number is always assumed to be 1. So what does that mean is, in terms of talking about the atmosphere radiation scheme, they always assume this lower boundary condition is a black body surface radiation. In other words, this emissivity, it doesn't change at all. It's just a black body radiation all the time. Okay. And in reality, there's also another module in the coupled GSM, which is the land surface model. So if you read the documentation, for example, the CESM, you will see this upward flux is actually what is one quantity which can be explicitly computed from the land surface model. So when the land surface model computes the upward flux at the surface, the way the CAM or the atmospheric radiation scheme interpreted it is, it will take this flux and convert it back to a so-called radiative skin temperature. So just say this is the flux computed by your land surface model. Then you assume this is the equivalent skin temperature. And then you put this one to the CAM radiation scheme, which is RTMG. And then you start the whole radiation transfer calculation in the atmosphere. So basically, you can see immediately the radiative skin temperature here might not be the true surface temperature. And the second is you can quickly see there could be some inconsistency here between how the different modules treat the surface emissivities. So you might ask, the GCM has been developed for more than 2 decades. So what's the traditional wisdom there? Just use the black body emissivity rather than actual realistic emissivity. And here is one chart to summarize. So basically, in reality, whatever the upward net flux from surface, the radiative flux, just the long wave, it can be split to 2 parts. The first part is the actual emission from the surface. The second part is the reflection of the downward flux from the atmosphere. And if you remember the textbook about radiative transfer, the Kirchhoff law, the emissivity equal to absorptivity. Then the reflectivity equal to 1 minus the absorptivity. So that means it's equal to 1 minus emissivity. So that means the net upward flux, which consists of these 2 components, can be written as this. So there are 2 facts. The first fact is this emissivity usually is very large, very close to 1. So that means 1 minus this emissivity is a small quantity. And the second fact is, if the downward flux is primarily coming from somewhere very close to surface, then this flux is very comparable to the black body radiation from surface. In other words, this downward flux might be very comparable to this. So if they are exactly the same, then you can say regardless what's the value of emissivity, this upward flux is always same as the black body radiation. But the fact is, for many frequencies, if this one is comparable to that, it will also very close to black body radiation. So that's actually basically the traditional wisdom there, say, to save up whatever the treatment there, let's just use the black body emissivity here. So the question here you might want to ask is this argument true for all the places and for all the frequencies? And if it's not true, what's the implication there? So that's the modeling consideration of the surface emissivity. But you can also get surface emitted from remote sensing or from in situ measurements. So what I showed here is the modest retrieval of just the land surface emissivity for 2 months, January 2008 and July 2008, and for 2 particular frequencies. So this is 8.3 microns. So that's normally what we talk about as the window band. So that's a band you have little atmosphere absorption there. And you can quickly identify the emissivity can be as low as 0.75 and as high, of course, as close to 1. And not only that, there is a seasonality there. For example, if you look at the Gobi Desert here and the associated neighbor area, you can see the change from January to July. And if you look at another frequency, for example, 12 micron, so which is around 800 wave number, you can see you also have this seasonality. So for this January, it's almost all close to 1, but here you will see some is as low as 0.93. So in reality, this surface emissivity is not a constant, and it could change with both time and the location and the frequencies. So now, if you take this into account, now the deal breaker is how true this one is, because we know in reality the surface emissivity is not 1. So if this one is still true for most of area and most of frequencies, then the previous treatment is still reasonable. The question is how good this one is. So that comes about so let's just leave it as a question mark there and now look at another fact between the reality and the model. So if you survey how the model treat cloud in the long wave radiation, and out of more than 20 plus GCM in the AR5, the normal file which has a treatment of the scattering in the long wave. And the primary argument there is the absorption effect of cloud is dominant for the long wave. And that's a reasonable statement in terms of the broadband average flux. But if you plot the imaginary part of the index of refraction for ice with respect to frequency, so basically the imaginary part of the index of refraction is where you're responsible for the absorption. The real part of this complex number is what is responsible to scattering. So you can see in this logarithmic plot, the imaginary part has a local minimum here in the far IR. So the far IR is defined as the frequency lower than about 600 wave number. So that's from 600 beyond. Normally we call it the thermal IR or middle IR. So if you have a local minimum here for this imaginary part, that implies you could have very strong scattering behavior here. So that's the first thing. So at least we can infer for some instance, scattering in some IR band would be important here. And actually, you can look at the GCM, even for the GCM who treat the scattering in the long wave, they have a different way to do it. For example, for Professor Zhou, use the scaling to do the treatment, and also some people try to implicitly include it in the two-stream way. And this impact of scattering is actually also dependent on how many water vapor you have in the atmosphere. So what I plot here is two simple calculations. Basically, what's showed here is the difference only in the far IR, so that's from 0 to 600 wave number. So only the difference between when you include scattering or you do not include scattering. And for two parts, the first is the OLR, so that is upward at the TOA, which shows in the dotted solid line. And the other one is the net flux at the surface. So you can see for the mid-latitude summer profile, when you have abundance of water vapor, so normally the total column of water vapor in the mid-latitude is about 2 centimeters there. So you can see you don't need 2 centimeters, even just 1.2 centimeters. This flux difference is already almost zero. And only when you put the cloud very, very high, in this case 5 kilometers, the flux difference is noticeable there, and it's around 1 watts per square meter there. But the situation would be different if you look at the subarctic winter or any polar region. The primary reason is water vapor is very small there. And because the water vapor is very small, then you get a lot of chance. The photon can be reflected and then can be absorbed. So in this case, you will see when you change the column water vapor from 0 to about 0.4 centimeters. So in the polar subarctic winter, the total column water vapor is only in the order of magnitude of millimeter, not centimeter at all. So now you can see for both the surface flux and the OLR, it will not converge to 0. So this situation coupled with another fact about the far IR. So far IR, as I mentioned, it just defined as one part of the infrared spectrum. And if you do a model calculation or if you count from observations, you ask the question, what percentage of OLR is coming from this spectral region rather than from mid-IR? It's actually about 50% of the OLR coming from this region. And if you remember another thing in the radiation transfer textbook, there's one law called the Weir's displacement law. So basically the law says the colder the temperature is, then you have more fraction of emission coming from far IR rather from mid-IR. And another fact is this phi r is the boundary between the IR and the microwave. And in terms of the molecular spectroscopy, this part is strongly dominated by the water vapor pure rotational depth. And as a result, normally this band is very opaque. So that means the optical depth is very large. But there are exceptions. The exceptions is when you have very cold and dry situation. The global averagely, the total column water vapor is about 2.2 centimeters. But if you go to the polar region, in the winter time, for example, in the plateau of Antarctica, you can get total column water vapor as small as 0.1 millimeter. So that's a difference by a factor of 100. And even you take the climatology in the Antarctic, the column water vapor there is just 3 to 5 millimeter there. So here I just give you an example. So even you don't look at the, just say, let's look the warmest places, the tropical clear sky. Okay. And then you calculate OLR. It's about 288 watts per square meter there. And if you want to break down it spectrally, the phi r is from 0 to here. So you can count about the contribution of the phi r to a tropical clear sky profile is about 100 watts per square meter out of 288. So that's about 33% of contribution from phi r. And when you're talking about cloud or you talk about the clear sky in a colder climate, this contribution can only increase rather than decrease. And here is just another chart to try to illustrate the point I just mentioned. So if you just calculate, when I change 1 degree of surface temperature, how much would be the change of the OLR in the phi r at the top of atmosphere? What you see is in the majority of globe is 0. The reason is the atmosphere is so opaque at that particular spectral region. So you increase surface or you decrease surface whatsoever, there's no impact for OLR at all. The only exception is the Antarctic, the Tibet Plateau, Greenland, so where you have very dry and cold atmosphere. So that's where the phi r is not opaque anymore. Even you change the surface temperature, you can directly see it from the top of atmosphere. So given how important the phi r is in terms of the radiation budget, actually truth is we never observe spectral radiance in the phi r from space beyond the 400 wave number. And even from 400 to 600, there's only a 10 months observation back in 1940s by a remarkable advanced instrument called IRIS, put together by Dr. Rudy Hansen from NASA Goddard. So, but there's another complexity. If you look at the remote sensing community, okay, they're using spectral emissivity all the time. That's the only way you can invert land surface temperature correctly. But still, because they never do observation here, so no people, in terms of the land remote sensing, no one cares what's the spectral emissivity beyond the 650 wave number. So for everyone, they just assume it's a constant number beyond 650. Okay. So it just says there's no measurements in phi r whatsoever. So when you put this couple of model reality contrast together, you can paint a different scenario between the model and the reality. So this is essentially the model world. You assume the emissivity in the phi r is always 1, and the reflectivity is always 0. And you assume for this cloud, the single scattering albedo is always 0. Just say it's no scattering at all. But in reality, this number could be smaller than 1. So in other words, the emissivity could be somewhere between 0 and 1. And this one could be scattering. So the single scattering albedo could be a non-zero number there. Okay? And if you look at the polar region, because the water vapor between the cloud and the surface is so small, so the scattering happened at the surface or the scattering happened at the base of cloud, they will not be totally absorbed by the water vapor in between. Instead, they can talk with each other. So whatever scattered here can be felt by surface, and the surface reflection of the long wave radiation can be filtered by the cloud here. Okay? So the question you want to ask is to the first order, you say, if you take this realistic treatment, how much it can change the radiation budget in the polar region for both TOA and the surface. And another quantity normally ignored by people when they study radiation budget, or at least not as extensively studied as TOA on surface, is this net absorption of radiation. So basically, if you take the difference between the OIR and the net upward flux from surface, that gives you what's the net emission from atmosphere, right? So that means radiatively the atmosphere is cooling, if that's a positive number. If it's a negative number, that means radiatively atmosphere is warming up by this radiative process. So basically, before we set out to do the studies, our working hypothesis here is, the first is the scattering by the cloud should reduce the OLR and increase the downward flux at here. So the rationale behind this is saying, in this scenario, if the flux is not absorbed, then it goes to the space. But in the scattering scenario, if the flux is not absorbed, it also has a chance to be reflected back rather than going to space. So that's the reason it will weaken the flux going to space. So that's the reason we think it will reduce the OIR. And at the same time, because you now have this branch of possibility for downward flux, so that will increase the downward flux to the surface as long as the water vapor absorption in between is small enough. And the second working hypothesis is also straightforward. Now you treat this emissivity being a number smaller than 1. So we assume the net upward flux will be smaller. Okay. So then in order to do this, the first is we must know what's the actual surface spectral emissivity there. And we do a radiative transfer calculation here. So basically, if you want to model the short wave albedo of snow, the independent scattering is enough, and that is what exactly Mark Flandern did for the snow physics module in the camp. So basically, because the wavelength here is smaller than the distance between two snow grains, so you can just still use Mie scattering and start from there. But for the IR emissivity, you do not have that simple assumption. The reason is now you are treating with the wavelength which is comparable, accurate, or even larger than the average distance between two snow grains. So in order to correctly model it, we have to use the scattering theory with respect to densely packed medium. So basically, in terms of the mathematics, you have to borrow this spatial correlation function from statistical mechanics, and then you come up with a factor called the structure correction factor. And then we can compute this spectral emissivity as a function of snow grain size. So in the GCM, like the CAM or CESM, the snow grain size is a prognostic variable computed from the snow physics module. Then they calculate the snow albedo also in a prognostic way. So here we can make it consistent, make the spectral emissivity being computed in the similar way. But there's the inconvenience truth. No one do any measurements in FIR. So even you have a model to simulate it, you cannot validate it directly. So the best way we can do is we calculate this spectral emissivity for all the long wave. Then we validate whatever they have in the mid IR. Then we can only trust, say, the FIR is what we computed here. So this is a chart from the paper published from my group. So basically, the solid line is the measurement by Dr. Hori from Japan, JAXA. So basically, they set out to go to the polar region, put a spectrometer there, and measure the spectral emissivity for the different snow. So the fine snow, medium snow, and the coarse snow. And the solid line is how they do the measurement from about 700 wave number and beyond. The dashed line is what we can simulate and try to match up with the observations. And beyond the flux form of the emissivity, you can also define the emissivity as a function of the veil zenith angle, and that is actually what can be directly measured here. So here is showed the same thing. The solid line is the measurements from the Dr. Hori's study, and the dashed line is what we can match up the different emissivity and the different angle here. So you can see the emissivity in the FIR, okay, is about, it's not 1, it's about 0.96 here for this case. Okay. So the sensitivity study we did here is we single out the Antarctic plateau. So basically the altitude higher than 2 kilometers there. And then we use the CloudSat Calypso joint retrieve the cloud water vapor content profile. And because the ice size was not retrieved here, so it's not confident enough. We don't have that much confidence. So we just assume a sensitivity study. We assume 2 typical different ice particle size there. And we take 1 winter month, and you can see that's the more than 500,000 of profile there. And actually 46% of them is clear sky. So the question here we are interested in not just the sensitivity for one individual cloud profile, but rather the monthly mean radiation budget here. And we use the retransfer model developed by AER, the RTM-LW, and this one can handle both the scattering and the surface spectral emissivity. And actually, we did all the calculations using Fourier code as well. And the bandwidth is not exactly the same, but the general results are all similar. So basically, this is the table which we summarize what we see there. So this case 0 is the assumption used in current GCM. It's black body surface and a non-scattering cloud. The case 3 is the case where you change only cloud, but you still assume surface being black body. And for all calculation, we tried the effective size of the ice droplet being 25 micron or 50 micron. So the interpretation for case 3 and the case 0 is just what we described before, or what our working hypothesis expected. So basically, now in addition to the branch going to the space, now you have a downward branch. So that's the reason it reduced in the monthly mean average sense, about 0.5 to 1 watts per square meter difference in OLR. And then it also increase the downward flux. So in other words, you decrease the net upward flux. So they just opposite to each other by definition. And as a result, it has an increase of net atmosphere absorption in FIR, or decrease in the FIR emissions. So when you include, again, the surface emissivity, that's for case 1 and the case 2. The difference between the 2 cases is one has a fine snow, the other has a coarse snow. So in that case, you really decrease the upward flux from surface. And that is actually make the change at the reduction of OLR even noticeable here, okay? And similarly, it changes the net upward flux here. And as a result, it also increase the net atmosphere absorption or decrease the net atmosphere emission. So basically, but because the change of this, so the net change for this column radiation is not as big as this scattering cloud. And you can do this calculation. For here, we just do it for the fire, but you can do this calculation for any band you want. So for all 12 bands in the RTMW, you can see the largest change is coming from a fire. When you look at the middle IR, the change is really, really small. And that's the reason, actually, the traditional wisdom when you people look at the mid-latitude, when the water vapor is so opaque, then here it also becomes smaller. But in the polar region in fire, this could make a difference here. Okay. So we essentially compute this fire surface emissivity and we evaluate this polar radiation budget. And then the people from Beer Collins group is interested in this study, so we collaborated further on this question. So basically, we end up with, we use different technique to compute the surface spectral emissivity, not just for the snow, but for all the land surface and the ocean surface. And we validate it against all the available measurements, primarily from this ASTER database. ASTER is a satellite to do the land surface, and because of that, they commissioned a large scale of laboratory spectroscopy study for the surface. So here I just show you a couple of examples. So this is what we simulated the spectral emissivity of the calm water surface. And the black one is what actually be measured by this ASTER project. Okay. And they only stopped at a 650 wave number, but actually if you beyond go to the fire, the emissivity drops a lot. And this is just one example for how well we can simulate the land. So for the land, most of the mineral there is silicate. So even the detailed chemical composition can be different, but the majority of the absorption feature here is actually quite consistent. And this is one measurement from the Planetary Surface Society, and we can try to model this one also to a highly consistent result. So basically, we can put up this so-called global surface spectral emissivity database for both fire and the middle IR as well. Here we just show you 4 different types: the ocean, desert, snow, and the vegetation. So for this one of vegetation, it's just too complicated for us to model it to a high confidence. So that's the reason we just take the whatever ASTER database can provide us and then just assume it's constant in the fire. And so basically, Beer Collins group, Dan Feldman, they incorporate what we provided here to the CESM. Also, they need to change the RTMG a little bit in order to consider the spectral emissivity. So here the study has no effect of long wave cloud scattering. It's just the surface emissivity. Okay. So they carried out 2 rounds. One just they run this RCP 8.5 scenario, so which has a very strong greenhouse forcing scenario. And the other one is they run this forcing scenario, and then they take the surface emissivity into account. Then they run it for 20 years and see how much the climate will difference in 20-year time frame. And here is essentially the change of the climate in the 2013s for the 2 simulations. So the first one is when you take the surface emissivity into account. The second one is you just assume it's black body radiation as in current CESM. So you don't need to look at here, just look at these two plots. So basically it says the surface temperature change can be as large as 2K there in the Arctic. And the frozen extent, so basically the CS fraction there, okay, can be reduced as much as 10% there. And also because of this, you have a series of teleconnection actions in other part of the globe. So let me try to summarize it. So basically, this is not new. So everyone aware of this bias in the GCM. So just say we treat the surface emissivity and the cloud scattering in the long wave in an approximate way. But here we just try to say we try to quantify how much that could affect the radiation budget. But there's another one which is known unknowns if I borrow a line from Ramsfield. So basically, we even don't know what's the truth in the fire. All we can do at this moment is do a faithful radiation transfer calculation and validate against the middle IR measurements. Then we try to say the fire should be like this. Okay? And the impact in terms of these two treatments on the monthly mean radiation budget is not small. It's very detectable there. And because of that, if you carry out a climate simulation over a long term, it would cause some effect on the climate change for both the thermodynamic local effect and the dynamic teleconnection effect. And because I'm a guy practicing all the from observation to modeling, so I also have some thought about how this really affect our climate observations. So here I'm trying to be a little bit provocative here. So we have many satellites in the space, but you can pick one of them and ask what's the primary objective of this satellite. And another of them is designed to be accurate enough to measure the climate change or monitor climate change. So we have many satellites, which is process-oriented satellite, or monitoring the mean state of climate, for example, the CS or the glaciers. But none of them is designed to be accurate enough to observe the climate change. So this poses an interesting question if you think from a fundamental physics way. The GCM is really a theoretically numerical tool to help you to make a prediction what would happen. But the only way to validate this is actually to observe the same thing. So this is exactly how the physics society has been doing. For example, one physicist predict there should be a Higgs boson particle there. Now they spend billions of dollars to build this LHC to validate there should be such particle in the space, in the reality. Okay, so the same thing here. So as of today, the mindset here is still the modeling people pick up whatever available observation to diagnose or validate the GCM. But I feel it should be the other way around. The modeling community should set out and make say this is precisely the measurement which we can use to distinguish the different GCM predictions. And from that perspective, I would argue say the most accurate and the most relevant measurement here is the spectral flux and the spectral radiance, because there are probably hundreds of thousands of ways for a GCM to be tuned to match the broadband flux. But there's no single way you can tune them to match thousands of channels of spectral observations. And this is actually also the fundamental quantity for a GCM. When you look at a climate change scenario, first question you want to ask is how much is the forcing, how much is the feedback in terms of the watts per square meter there. And that's exactly the radiometric quantities. And if GCM cannot agree on those quantities, then the further implication on precipitation, flood, all the other thing is a effect from those quantities. Okay. So if those quantities cannot be monitored and observed and cannot be used to gauge the different GCM, then the secondary prediction from GCM would be even harder to distinguish from each other. So I guess that's it. Thank you.
Xiang-Lei, nice talk. I really enjoyed it. So when you say you use cloud set and Clipso to do the Hui Liao, so are you, what data are you using? You're using ice and liquid retrieval?
Yes, yeah. So,
So
basically, all retrievals have problems in the polar region.
Okay.
So it's here. It's really a sensitivity study. We are not trying to pin down exactly number, but say, given this is a reasonable global, it's a reasonable observation with enough spatial coverage rather than just one line from
so
arm
it's kind
observation.
of the sensitivity like a difference to see how the change is.
Yes, yeah.
Thank you.
Yeah.
Xiang-Lei, I have a question about the CSM RCP simulation you just showed at the end. Can you go back to the plot? Because I happen to look at something similar to this. Is that like how long is the simulation? You just take the difference between two simulations, I suppose.
So this is simulation run by Dan Feldman, and to my best understanding, he runs this just as same as what exactly RCP 8.5 should be run, and he stopped at 2013 and look at the difference.
Okay, so it's like a 30-year difference?
Yes.
Okay.
Oh, no, I'm sorry. For this one, it's only the difference in the 10-year from 2030 to 2040.
So it's a 10-year average?
Yeah.
Did you do any like statistical analysis to make sure this is actually significant? Because if you perturb the system in any way, you are going to get some temperature difference.
Yes.
I'm not going to show tomorrow, but we just added in like the forcing due to aviation emissions. Fairly small forcing. You are going to get something like
Yes.
So
yeah, I agree.
I don't know
So
if I'm looking at noise or
yeah.
this is really
So
significant.
you have a good point. So one Dan actually is my contribution to this paper is really we calculate this, and Dan carried out to do this. And when he wrote up this paper, I tried to push him to give more physical diagnostic here. But if you read this paper, there are not too many diagnostics there. But the hypothesis, the leading hypothesis they put there is the same. So think about the CS, albedo feedback. It's really only working in the polar day, right? In the polar net, you have no that at all. But now the CS in the polar net even, it should not give up long wave flux as much as it should be in your polar region. So just like you said, it's very likely you are doing a perturbation in a part of a climate system which is very sensitive. And then you can get all those kind of difference. But to what extent this can be corroborated by physical mechanisms and by the physical robustness, I agree with you. It definitely needs further diagnostics. And actually, that's the reason DOE found us to further do this.
I can just go and make a quick recommendation, a suggestion. Just if you have like a 10-year simulation, you can just do a t-test to see if your difference is actually significant. It's not 1 year. You have some statistics to look at.
I think they did do the t-test. If you look carefully, they have some hashed area.
Okay.
That's a t-test.
Okay, that's good.
Yeah.
Thank you.
Yeah.
I think this is actually very relevant to the modeling community. I recall I went to a GWEX meeting in July in the Netherlands. Kevin Chambers, I'm sure you have read his papers talking about the global averaged surface atmosphere and top atmosphere energy balance. He said surface energy balance is wrong in many papers and all models, but not well known. He also said energy imbalance is a fundamental issue that needs more attention. So that's very consistent with what you presented here today. But I really don't know what we have a way forward, given all the analysis, all the models are wrong,
Yes,
and
I agree.
we don't have enough measurements. So what can we do?
Yeah, so I think Kevin Chambers here is a little bit over exaggerate. So what he is trying to seek is actually the sensitivity of the OLR or all the radiation budget with respect to surface emissivity. That sensitivity is small because the polar here is really not that much if you just do a simple average of the OLR over globe. So I think he is trying to dig in all the possibility for his imbalance argument. But at the same time, I think because the local radiation effect is not small and it can have further implications. And in terms of your question, what's the way forward? I would say, I don't know, because we have a dilemma here. We know a lot of necessary conditions in order to make a good climate model simulation. But we don't know what's the sufficient condition in order to make a solid climate change projection. And we don't even know whether such sufficient condition exists or not. So think about 20 years or 30 years ago. Model is just theoretically to help you to thinking, to decipher the physical mechanisms. Now when you try to put it in such rigorous mission to projection, mitigation, adaptation, we don't have a bar there, say which model can pass to do this, which model cannot pass to do it. That's the reason I'm thinking the climate observational society should be heard, say what model need or what's the ultimate test you can apply there to say this model is good enough, at least from the energy perspective, to do blah, 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 rather than say each model can also give you a different scenario, like just average everything, get an ensemble there. So, yeah.
Because of time limit, so let's discuss offline. Thank you.
I'm very interested in those spectral variations for different.
So because of time limit, so we have to stop here. So please discuss it offline.
Can you show that figure? The spectral variations are different for oceans. For oceans, it's except for those small wave numbers, the emissivity is close to 0.97, and that's what most people use. Okay? But for the wave numbers smaller than 1,000 or so, it's much smaller.
So here is about only 200 wave number. So here is smaller, yeah. But it's my argument there. If you are in the tropics, it doesn't change that much because the downward flux is so close to surface, so it won't.
Yeah, but in other regions, effect could be very large.
Yes.
My question is, how confidence do we have in those dashed curve areas?
So. And again, we have no measurement here. So we validate this not against EST, we also validate against many other observations. Just say this part we have high confidence. But if you are talking about here, because there's no measurement for us to validate that.
Okay, thanks. Yeah.